All right, we're back. We're talking about uniform acceleration. There's definitely a difference between uniform acceleration and uniform motion, which is we discussed last time. Remember, uniform motion is constant velocity, keeping with a constant speed in a constant direction, where acceleration is going to be quite different. So what exactly is acceleration? Well, if you speed up or slow down or change direction, you basically are accelerating, which is good to know. But also, it is the total rate of change of velocity. And we're going to get into how to figure that out here in just a second. But it is a vector quantity, so make sure that we realize that direction is going to be important. And though we've been dealing with units already, meters per second squared is what we're going to use for our units for acceleration. The actual equation for acceleration is going to be your final velocity minus your initial velocity divided by the time. And since velocity is meters per second and time is in seconds, you can see how you end up getting your meters per second squared as your units. Now, acceleration can change in a couple different ways. You can either speed up or slow down, or you can change your direction, or you can do both. Speed up, slow down, or change direction. Either way, you are accelerating. If you think about you going to school this morning, whether you took a bus or a car ride or walked, the idea is that you accelerated. You had to definitely speed up from a resting point. You had to slow down when you got to school or maybe at a stoplight, and you had to turn in or change direction to do so. So you were accelerating quite a bit. In fact, acceleration is more natural than that idea of uniform motion that we were talking about earlier. Uniform acceleration is specifically meaning that there's equal changes in velocity. The idea that your acceleration is pretty much staying constant, which means that your velocity is changing at equal intervals, which gives it more of a straight line or direct relationship, if you will. The idea, of course, is that since your displacement is going to be increasing rapidly, your velocity changes, and because your velocity is consistently changing, you have a constant acceleration. Going back to these graphs, we do need to pay attention more now to the labels, since we have more than one graph we have to look at. Position versus time graphs are important because there's a parabolic relationship when we deal with acceleration. If you recall from our previous lab, we dealt with uniform acceleration, which was a straight line. That idea gave you constant velocity. But now that we have a parabolic relationship, it means the velocity is consistently changing, which gives us our uniform acceleration idea. Don't forget that the slope on a position versus time graph, since it's change in y over change in x, is really just giving you meters per second, which really is your average velocity. So keep that in mind for future data analysis. If you want to look at a velocity versus time graph, velocity is in meters per second and time is in seconds. The relationship for uniform acceleration is shown because velocity has a nice direct relationship, an increase over time. If you take the slope of this line, once again, remember slope is change in y over change in x, then you get the units of meters per second per second. Let me see if I can squeeze that in there. Meters per second, which really just gives you meters per second squared. Meters per second squared is really just the units for acceleration. So once again, by taking the slope of one of our graphs, we can actually determine even more information by using the slope. It's not just busy work. For more on velocity versus time graphs, if you are speeding up, you could be speeding up in the positive direction, or in this case, speeding up in the negative direction. Either way, both of these graphs are considered speeding up. Just one's forward and one's backwards. If you want to talk about slowing down, you look at these two graphs. These guys are slowing down because their velocities are decreasing closer to zero. This one is moving forwards and this one is moving backwards, but either way, they both are considered slowing down, something that we'll have to get used to and have to pay attention to the fact that this is a velocity time graph, not a position time graph. Also mentioned over here, but might not be able to see it, another name for slowing down is deceleration or decelerating. So often you'll hear us talking about accelerating for speeding up and decelerating for slowing down. Keep that in mind. Now, the direction of acceleration will become more and more important, but if you are speeding up, then we can say that both the object's direction and acceleration are going in the same direction. Kind of like acceleration is helping you out, though acceleration is not a force. Later on in the year, we're going to see the relationship between force, mass, and acceleration, and the direction of the acceleration will make a big difference. So more later in the months when we get to know a little bit more about that. As for slowing down or decelerating, if your object is moving forward but you're slowing down, then acceleration is moving in the opposite direction, opposing the motion. You can see that down here. Right here, a car is speeding up. Velocity tells you what direction the car is moving in, but still, since it's speeding up, acceleration is working with it. If the car is slowing down and still going in that same direction, acceleration is going opposite of that, against it. It's important to know the directions of acceleration. One last thing, we haven't graphed anything with acceleration versus time, but since we're dealing with only uniform acceleration, our acceleration graphs will always look like this, a flat, no relation kind of graph, or a constant. The idea behind that is, since the velocity is changing at equal intervals per time, acceleration stays constant. If you do take the area underneath this curve, though, if you look at it, we know area is length times width for a rectangle. Acceleration is going to be in meters per second squared. And when you multiply that by the length, which is time, you multiply those together, seconds cancel out to a certain extent, and you're left with meters per second. So by finding the area underneath your curve for acceleration versus time, you actually are finding velocity. Yet another little surprise from graphical analysis. So we're about to wrap up acceleration, but remember, your acceleration is really just your final velocity minus your initial over time. If we look at this example, it goes from 9 seconds to 12 seconds, which really is just a total of 3 seconds. The initial velocity is a positive 28 meters per second, and the final velocity is a positive 13 meters per second. If we plug in final velocity of 13 meters per second, an initial velocity of 28 meters per second, and a time of 3 seconds, what we should end up with is, if I can write it over here, well, it's going to be 13 minus 28, so you're going to get a negative 15 on top divided by 3. So you'll end up getting a negative 5 for your acceleration. Now, looking at this problem, this is a car that's moving forward, but it's slowing down because it went from 28 meters per second to 13 meters per second. That's considered deceleration. So it's no surprise that if our car is moving forward and it's decelerating, that our acceleration would be in the negative direction. So therefore, since the car was moving forward, velocity was forward, and it's slowing down, acceleration was therefore moving backwards. You guys got this worksheet, or we worked on this in class, but we also have other problems on worksheets. So make sure you're getting that right with your direction. Remember, positives forward, negatives backwards. But this concludes our talk on acceleration. The idea is that the change in velocity over time is going to give you that. And we're going to do a lab on that to make sure that we understand exactly what acceleration is and also how all these different graphs relate to each other. Thanks for listening. Have a good one, and good luck with your physics.